Good morning, everyone. Hi, how are you? I'm making this video because there's a really bad plague going on in the dissident white right, and that is about flat Earth, and people are getting sucked into this flat Earth shit and believing in flat Earth, and making claims that the Earth isn't round, and going even further and saying that things like geometry and astronomy are Freemason sciences and things like that, and to try to even prove that the Earth is flat, even though we have all the scientific evidence. It's all mysticism according to these people. And I've even heard them say things like, we know the Earth is round because we can predict solar eclipses. And he's like, oh, those are the historical ones were faked, or the history was tampered with, and then the modern ones are holographic illusions and stuff like that. Just absolutely insane stuff. I don't know where this is coming from. I actually was talking to ChatGPT about this, and she was just basically saying it's like an ultimate rebellion. Sometimes these people don't even believe it themselves, but it's just the ultimate rebellion against authority because you don't even believe their science. And even George said that to me, that same sentiment. And it's a pretty big thing. Anyway, the beginning of this, I got to get a couple things done. First of all, let me make sure that this is playing properly on, what's it called? Let's make sure this is playing properly and the sound is fine so that there's no problem. Yes, it is. And okay, and then let me put this on Telegram if I can. If it'll let me in. Sometimes I don't want to have to go on my phone. I can't go on my phone right now. Okay, give me 1 second. Hold on. As I joined this new thing with Jord and Lewis, the Cube, as you can see, it's called. It's this new channel, and this is where I'm meeting a lot of these people. So anyway, this all started. So I actually wrote a paper in college about the movement of the Earth. So I wrote 2 papers. So I'm going to say the same thing over and over again a bunch of times throughout this, because it is the evidence that we have that our system, our global Earth, heliocentric, sun-centered universe or solar system is accurate. Okay. We believe the Earth is a globe. We believe that the Earth goes around the sun and the moon goes around the Earth. If that is true, we make a model of that, and we place where the moon is, we place where the sun is, we place where the other planets are, and we place where the stars are. From the position that then we say the Earth is going this fast, we determine what position it's in, and we determine where the moon is. From this, we can predict accurately 100% every night and every day and every year where the other planets are going to be in the sky, where the stars are going to be in the sky, the change of the seasons, the change of day and what time it's going to be where and when, the eclipses of the moon, the eclipses of the sun, the tides. So if this is all true, we're saying this is the way things should work, and it does work that way. It works exactly as the models say it does. Now, flat earthers cannot make a model that can predict all of these things at all. It's impossible. There's no way. Yeah, they throw this off as, of course, they have to relate to saying these are Freemason sciences and it's all manipulated and things like that, because they don't have that power, right? They don't have the power of prediction, and science is about prediction. If you've predicted the future state of something, then you have understood it and you have shown that you understood it. If you can predict it 100% every time, if you always know its velocity, its acceleration, its mass, and you always know where it's going to be and where it's going to land, and precisely where it's going to land, and what kind of impact it's going to have, and how much of a dent it's going to make, and how much will it deform, and things like that. If you can get all that down, then you understood it. And nobody really denies that physical science, when it comes to non-celestial bodies, is real. So it's just when we start coming to celestial bodies that we say it's not real. Because you've never been to space, you've never seen it in space, you can't actually measure it in space. You can't measure it, but you can make predictions about where everything's going to be and when and where. And you can't get into outer space, but you can use a telescope to see where things are, and they're always there where they're supposed to be. So anyway, okay, so this is a paper I wrote called Galilean Defense of the Heliocentric Model. So here are a few things that Galileo said to prove that the Earth was round. So in order for Galileo to defend the heliocentric model of the universe, he first had to refute the reasonable argument put forth by the geocentric Ptolemaic system. If the heliocentric model was true, the Earth would have to be rotating on its axis and revolving around the sun. It is important to note that in Galileo's time there had not been a defined Newtonian law of inertia. Every body continues in its state of rest or of uniform motion in a right line unless it is compelled to change that state by forces impressed upon it. To the scientists of Galileo's day, if the Earth was both rotating and revolving, there were several reasonable questions that could be asked. One frequent question was, why do not flying birds not fall behind the Earth as it revolves around the sun? Galileo successfully answered this question by demonstrating that on a moving ship, a rock released from the top of the mast will fall at the bottom of the mast, the same as a motionless ship. Another legitimate question was, why don't objects fly off the spinning Earth? Galileo answered this question by referring that when a body subject to circular motion is released, it has the tendency to move along a straight line tangent to the point of release. Though he did not have the law of inertia, Galileo was able to use common knowledge of the day to eloquently argue this position. So, okay, you can't use arguments like birds don't fly behind the Earth or things like that to prove that the Earth is flat, because, like, as I said, with the ship and the mast and things like that, if you're going at that speed, then well, I think he explained it really well. Even after Galileo began, there were logical reasons to believe that at least some of the planets revolved around the sun rather than the Earth. It was known that the outer planets of Mars, Jupiter, and Saturn went through great variation in distance relative to both the sun and the Earth. These variations were so significant that when Mars was closest, it appeared 60 times larger than when it was farthest. In contrast, each extreme variation in distance relative to the sun and the Earth were not noticed in the inner planets of Venus and Mercury. It was also known that during their planetary orbits, the outer planets could only be seen beyond the sun. The inner planets of the Venus could only be seen beyond the sun, but the inner planets of Venus and Mercury could sometimes be seen beyond the sun, but sometimes be seen between the sun and the Earth. From this knowledge, it was logical to deduce that at least Venus and Mercury could revolve around the sun. If it was true, it was logical to expect Venus and Mercury to have observable shape change phases as they orbited the sun, similar to the moon, and no such phases of Venus and Mercury had ever been observed. With his invention of the telescope, Galileo discovered the sequential, cyclical, and incremental shape-changing phases of Venus, which has not been observed with the naked eye due to the extreme long periods of Venus' shape-changing cycle. Thus, Galileo provided conclusive empirical evidence that Venus revolves around the sun. So we know other planets revolve around the sun. And you know, yeah, we know that other planets revolve around the sun, as was shown with Venus and Mars, which became obvious because they're the inner planets, right? They're actually closer to the sun than the outer planets. And I guess maybe, yeah, you can't see the outer planets because, well, you could only see them on the other side of the sun because the light is reflecting back to Earth, right? When it's on the other side of the sun. But if it's on your side of the sun, the side that you're facing is not reflecting light. So, or it's actually behind you. Actually, yeah, you can. The Earth is behind you or something. Actually, wait, let me think about that for a second. Okay, when it's actually right, when it's on the other side of the sun, so it's the sun, right? It's reflecting. Whereas when it's on the other side, the Earth is in between the planet and the sun. And why does it disappear? That's an interesting question. Actually, okay, let's entertain that question. Let me go over here and let me show my. Let's see if I can. How do I tilt that? Why isn't it? Why isn't that working? Give me 1 second. I don't know why this is this way. I don't know why it won't. Why won't it go the way it's supposed to go? Shit. Give me 1 second. Okay, that's not working. Actually, okay, let's actually give me 1 second. Let's actually ask, you know, why can't you see the outer planets when they are not on the other side of the sun? See what it says. Astronomers are unable to see planets around other stars because the stars they orbit are millions of times brighter than the planets themselves. Any light that reflects off the planet or heat radiation from the planet itself is drowned out by the massive amount of radiation coming from its host star. Planets are also too small to observe from a distance, and they are not bright enough to be observed from Earth. Okay, astronomers are unable to see planets around other stars because what's other stars? Meaning not the planet, not the sun. Because the stars they orbit are millions of times brighter than the planets themselves. Okay. So, okay. Anyway, the point is that there's only a certain, you can only see the outer planets a period of the time, only half of the time. Whereas the inner planets you can see all of the time with, especially with the telescope. And that's because the inner planets are closer to the sun. So it's the only time where a planet is in between the sun and the earth. There's no other time when a planet is in between the sun and the earth. And those inner planets go through eclipses like the moon. Now, I don't quite understand how those eclipses prove that they are revolving. I don't know enough physics yet. Hopefully that will improve. And actually, we're going to be going through that in today's lesson on astronomy. But somehow, I know that obviously the eclipses of the moon can be used to prove that the Earth is round. but I'm not 100% sure. But let's just trust the astronomers to say that right now, if I can prove the moon going through phases proves circular motion around the planet, then Mercury and Venus going through phases, going around the inner planets, can somehow show with geometry that the inner planets are revolving around the sun. So we know that there are at least 2 planets revolving around the sun from their elliptical orbits. Hold on. Okay, actually, I made a mistake here. Okay. Assuming that natural laws are as simple as possible, Galileo demonstrated that the Copernican geocentric model provided the least complicated explanation for the apparent retrograde motion of other planets of Mars and Jupiter. From an early perspective, astronomers believed that outer planets like Mars and Jupiter could often slow down, stop, or even seem to move backward. Ptolemy had created a series of extremely complicated diagrams and equations, which will not be detailed here, in order to try to explain the phenomenon of retrograde. Not only was the Ptolemaic heuristic model cumbersome, it was not very good at making accurate predictions about retrograde motion. Galileo argued that if the heliocentric model was true, the apparent retrograde motion of the planets were easily explainable as an optical illusion. Since Earth was closer to the sun, then both Mars and Jupiter had a smaller orbit, and so it would have a shorter revolution period. The observation of apparent retrograde was simply Earth overtaking the outer planets in their orbital courses around the sun. Okay, so the thing about the Ptolemaic system, anything, whether it's Ptolemaic or it's flat Earth, if you're going to try to explain things in the sky with the global heliocentric model, you can predict it easily with the same equation all the time. So with retrograde motion, since Mars and Jupiter are further out away from Earth has a smaller rotation pattern, so it's going to get around the Earth faster. And if you take that into consideration and you make a calculation based on a heliocentric global model, you could predict every time when Venus and Mars are going to go into retrograde. With the other planets, you can't do it, and you have to make very cumbersome calculations and exceptions all the time for when planets don't move properly. And even then, still with all those exceptions, you can still never fully accurately predict where Mars and Jupiter are going to be. And we have to, so it basically is another example about how all the planets, including Earth, are going around the sun in a very simple manner, right? It just simply explains it, and you can always predict where they're going to be in the sky all the time. So why should I give that model up for a model that doesn't make these predictions or makes them falsely, and it makes it overly complicated and it doesn't really work? Okay. Galileo discovery of Jupiter's moons did not provide direct evidence for the Copernicus heliocentric model so much as it displayed the immaturity of Ptolemaic geocentric model's explanation of the universe. It was already known at the time that the periods of the planetary revolutions proportionally increased as their orbits, presumably around the Earth, grew larger. However, the idea that revolution periods were proportional to orbital size in any instance where several bodies were revolving around a central body was not considered a uniform law of nature, since there was no other known instance of several bodies revolving around a common center. It was assumed by the disciples of Ptolemy that this law of revolutionary orbital proportion was unique to the planets revolving around the Earth. However, when Galileo discovered 4 moons orbiting Jupiter in 1610, he also discovered that the revolution periods of the moons also proportionally increased as their orbits grew larger. This discovery happened the sacredness of the Ptolemaic model by showing that if the planets revolved around the Earth was not the only orbital center in the universe, and that other orbital systems followed the same laws, making the whole system more natural and less excludingly unique. Okay, so first of all, the moons of Jupiter, when they were discovered by Galileo, proved that things orbited around other things other than the Earth. So the idea was everything orbits around the Earth is the center. Okay, but moons orbit around Jupiter, so Jupiter's the center for at least those moons. So it destroyed the idea that we were special and that absolutely every heavenly body on Earth revolved around us. But also what was found was that when the moons, the further out moons, it did take longer for them to revolve around Jupiter, and the inner moons revolved faster. And so basically what they were saying is that what they were seeing, what they thought was going around the Earth, at least they had it right. And they said that the larger the orbit, the higher or faster the or the longer it takes for it to revolve around Earth. And they found the same thing with they found the same thing with the moons of Jupiter, the ones that were further out. It took longer for them to revolve around Jupiter. So they said that everything was the same. There was these universal laws, and you don't want universal laws, because if there's universal static laws where everything's going to be in all times, it's no longer this kind of like mystical, irrational system where there's all these different loopholes and different unique calculations and unique appearances that can't really be understood by natural science. Well, everything operates on natural science, right? Even the moons that don't go around the Earth, they follow a predictable pattern, and because you can see them going around, you can actually predict them. And the phases of the moons and going around Jupiter, or I don't know if there are phases of the moon that go around Jupiter. I'm sure there is from Jupiter's perspective, but okay, that's enough on that. Okay, Galileo's assertion of how ocean tides proves the Earth. Okay, okay, not ocean tides. Let's not talk about ocean tides, because he actually got that wrong. Okay, so today, and we're going to be talking about. So if you see this picture, if the Earth revolves around the sun and we have Earth's orbit, we're going to be able to predict the times of day accurately, where it's going to be night and when it's going to be night. Obviously, the day side faces the sun, and the night side faces away from the sun. And with this a heliocentric global model, with the moon revolving around the Earth, we can tell that we can predict with accuracy when it's going to be in day and night. Flat earthers can't do that. Phases of the moon, as the moon orbits and goes in between the sun or away from the sun, we can tell when the phases of the moon are going to be, when it will be full, when it will be a new moon, when there will be an eclipse of the moon, and things like that. So there's phases of the moon. The seasons, we always know exactly when the seasons are going to come in, because it has to do with the tilt of the Earth. And when the sun, when you're facing toward the sun, the strong side of the sun, then you have summer. When you're facing away from the sun, or you're in the lower quadrant that is further away from the sun and is not getting direct rays, then it is colder and it is winter. So we can see that. And when you're basically the sun is equally hitting the North Pole and the South Pole because of its position, then you have the equinoxes and you have moderate in between temperatures. And then there's the solar eclipses. A solar eclipse happens when the moon is in between the sun and the Earth. But what's even better at predicting, or we know, not only see this little dot, the umbra, we know where there's going to be a total eclipse of the sun, but we also know where there's going to be a partial eclipse of the sun and how much it will eclipse. So we are able to predict that with absolute accuracy using the global model. Okay, so let's now go to what we're going to be going over today. Let's see. Give me 1 second. What we're going to be going over today. Just give me a second. Give me a second. Why can't I see? Okay, never mind. I have an astronomy textbook, and we're gonna deep dive on this and really try to understand this from scientific, geometric, astronomical. Okay, orbits and gravity. So we're going to start with the laws of planetary motion. Okay. We're going to learn about, describe how Tycho Brahe and Johannes Kepler contributed to our understanding of how planets move around the sun, explain Kepler's 3 laws of planetary motion. At about the time that Galileo was beginning his experiments with falling bodies, the efforts of 2 other scientists dramatically advanced our understanding of the motion of the planets. These 2 astronomers were the observer Tycho Brahe and mathematician Johannes Kepler. Together, they observed the speculation of Copernicus on a sound mathematical basis and paved the way for the work of Isaac Newton in the next century. Tycho Brahe's observation. 3 years after the publication of Copernicus De Revolutionibus, Tycho Brahe was born to a family of Danish nobility. He developed an early interest in astronomy and as a young man made significant astronomical observations. Among these were a careful study of what we now know as the exploding star that flared up the great brilliance in the night sky. His growing reputation gained him the patronage of Danish King Frederick II, and at the age of 30, Brahe was able to establish a fine astronomical observatory in the North Sea island of Hven. Brahe was the last and greatest of the pre-telescopic observers in Europe. So here, I think this is Tycho Brahe, and this is Johannes Kepler, their pictures or at least paintings. At Hven, Brahe made a continuous record of the position of the sun, moon, and planets for almost 20 years. His extensive and precise observations enabled him to note the positions of the planets varied from those given in public tables, which were based on the work of Ptolemy. These data were extremely valuable, but Brahe didn't have the ability to analyze them and develop a better model than what Ptolemy had published. He was further inhibited because he was an extravagant, cantankerous fellow, and he accumulated enemies among government officials. When his patron Frederick II died in 1597, Brahe lost his political base and decided to leave Denmark. He took up residence in Prague, where he became court astronomer to Emperor Rudolf of Bohemia. There, in the year before his death, Brahe found the most able young mathematician Johannes Kepler to assist him in analyzing his extensive planetary data. So remember, as I already said, the Ptolemaic model, even with all those types of insertions of irregulars, even he was still able to find lots of instances where the Ptolemaic system didn't exist, and these were published in public books. And so the public books were wrong. Johannes Kepler. Johannes Kepler was born into a poor family in the German province of Württemberg and lived much of his life in the turmoil of the 30 Years' War. He attended university at Tübingen and studied for a theological career. There he learned the principles of Copernicus' system and he became converted to the heliocentric hypothesis. Eventually, Kepler went to Prague and serve as an assistant to Brahe, who sent him to work trying to find a satisfactory theory of planetary motion, one that was compatible with the long series of observations made at Heaven. Braque was reluctant to provide Kepler with much material at any one time for fear that Kepler would discover the secrets of the universe motion by himself, thereby robbing Braque of some of the glory. Only after Braque's death in 1601 did Kepler get full possession of the priceless records. Their study occupied most of Kepler's time for more than 20 years. Throughout his analysis of the motion of the planets, Kepler developed a series of principles now known as Kepler's three laws, which describe the behavior of planets based on their paths throughout space. The first two laws of planetary motion were published in 1609 in the New Astronomy. Their discovery was a profound step in the development of modern science. The first two laws of planetary motion. The planet of an object through space is called the orbit. Kepler initially assumed that the orbits of planets were circular, but doing so did not allow him to find orbits that were consistent with Braque's observation. Working with the data for Mars, he eventually discovered that the orbits of the planet had the shape of somewhat flattened circles or ellipses. Next to the circle, the ellipses is the simplest kind of closed curve along to a family of curves known as conic sections. So, okay, I don't think he's talking about when you come down to this section here, but you could see this ellipse is oblong where this is circular. And they believed at the time, I guess they thought, oh, well, the simplest thing is for all the stars and planets and everything to revolve around the Earth. In circular pattern rather than ellipses, but he found that if they go in ellipses, you might recall from the math classes that in the circle, the center is a spherical point. The distance from the center of anywhere in a circle is exactly the same. In an ellipse, the sum of the distance from two special points inside the ellipse to any point on the ellipse is always the same. These 2 points inside the ellipse are called its foci, singular focus, or word invented to this purpose by Kepler. This property suggests a simple way to draw an ellipse. We draw the ends of the loops of strings around two tacks pushed through a sheet of paper into a drawing board so that the string is slack. If we push a pencil against the string and make the string taut and then slide the pencil around the string all around the tack, the curve that ellipses, that is an ellipse at the one point where the pencil may be. The sum of the distance from the pencil of the two tacks is a constant length. The length of the string, the tacks are at the two foci of the ellipse. Okay, we're going to look at this here. The widest diameter of the ellipse is called the major axis. Having this distance, that is the distance from the center of the ellipse to one point, is the semi-major axis, which is usually used to specify the time of the ellipse. For example, the semi-major axis of the orbit of Mars, which is also the planetary average distance from the sun, is 228 million kilometers. Okay. Okay, this looks like a circle. Drawing an ellipse. We can construct an ellipse by pushing two tacks, the white objects, into a piece of paper on a drawing board and then looping a string around the tacks. Each tack represents a focus of the ellipse, which one of the tacks being the sun. Stretching the string tight around a pencil and then moving the pencil around the tacks, the length of the single remains the same, so that the sum of the distance from any point in the ellipse is the foci is always constant. In this instruction, each semi-major axis is denoted. The distance of 2a is called the major axis of the ellipse. Okay, so looking at this, one of these tacks is the sun. So one is when the Earth, or when Mars or the planet, which has an elliptical orbit, is going around the sun, it's going to be closer to when it's on this side, it's very close to the sun, but when it's on this side, it's very far from the sun, because only one tack is the sun. And so the idea that they were circular meant that the planet was always an equal distance away from the sun, but he found that just wasn't the case. The shape, roundness of an ellipse depends on how close together the two foci are compared with the major axis. The ratio of the distance between the foci to the length of the major axis is called the eccentricity of the ellipse. The foci or tacks are moved to the same state when the distance between the two foci are to be 0. This means that the eccentricity is 0 and the ellipse is just a circle. Thus, a circle can be called an ellipse of 0 eccentricity. In the circle, the semi-major axis would be the radius. Next, we can make an ellipse of various elongations or extended lengths by varying the spaces of the tacks as long as they are not further apart from the length of the string. The greater the eccentricity, the more elongated the ellipse, up to the maximum and eccentricity of 1, where the ellipse becomes flat, the other extreme form of a circle. Okay, so obviously we're saying that the closer these are together, the more round the ellipse and the less elongated it is. And so even with those ellipses, you could predict the eccentricity of these planets, so you're able to make mathematical understanding of these planets, and it basically falls into a natural mathematical geometrical pattern rather than some kind of willy-nilly thing, and it all makes sense mathematically. The size and shape of an ellipse are completely specified by its semi-major axis and its eccentricity. Using Brache's model, Kepler found that Mars has an elliptical orbit with the sun at one foci. The other focus is empty. The eccentricity of the orbit of the Mars is only 0.01. Its orbit drawn to scale would be practically indistinguishable from a circle, but the distance turned out to be critical for understanding planetary motion. Kepler generalized this result in his first law and said that the orbits of the planet are ellipses. Here was a decisive moment in the history of the human thought. It was not necessary to have any circle in order to have an acceptable cosmos. The universe could be a bit more complex than the Greek philosophers had wanted it to be. So, anyway, mathematics saves today. Kepler's second law with the speed, which was each planet moves along its ellipses, also known as its orbital speed. Working with Brache's observation of Mars, Kepler discovered that the planets speed up as it comes closer to the sun and slows down as it pulls away from the sun. He expresses the precise form of relationship by imagining that the sun and Mars are connected by a straight elastic line. When Mars is closer to the sun, position 1 and 2 in figure 3.5, the elastic line is not stretched as much and the planet moves rapidly further from the sun, as in position of 3 and 4. The line is stretched a lot and the planet does not move so fast. As Mars travels in the elliptical orbit around the sun, the elastic line sweeps out areas of the ellipse as it moves. The color region in our figure, Kepler found that in equal intervals of time, the areas swept out in space by this imaginary line are always equal. That is, the area of region B from 1 to 2 is the same as the area of from 3 to 4. If the planets revolve in a circular orbit, the elastic line is always stretched the same amount, and the planet moves at a distance speed around its orbit. But as Kepler discovered, in most orbits, that speed of the planet orbit is its star or moon orbits its planet tend to vary because the orbit is elliptical. So obviously it's going to take, okay, I don't 100% understand this mathematics. I haven't taken geometry or algebra in a long time, though I'm going to be fixing that relatively soon. But the point is that from the observation, it either seems to go faster or actually does go faster. I can't understand. Anyway, the point is whether it goes faster or the planets have the same speed going around the sun, or if it really does speed up. And I think that has something to do with gravity pulling it in faster because it's closer to the sun. Though I have to look into that a little bit deeper. It makes sense. And if it's elliptical, at least you can predict the optical illusion. If it's an optical illusion, if it really is physically going faster, which I don't understand, then which might have to do with the gravity of the sun, then you can always predict that optical illusion or reality of it going faster. So in Kepler's second law, the law of equal areas, the orbital speed of the planet traveling around the sun, the circular object inside the ellipse, varies in such a way that in equal intervals of time, a line between the sun and a planetary sweep out equal areas. Note that the eccentricities of the planet orbit in our solar system are not substantially less than shown in our orbit system are substantially less than shown here. So they're just saying that the ellipse is a lot less extreme. Kepler's third law of motion, or astronomical third law. Kepler's first two laws of planetary motion describe the shape of the planet's orbit and allow us to calculate the speed of its motion at any point in the orbit. Kepler was pleased to have discovered such fundamental rules, but they did not satisfy his question to fully understand planetary motion. He wanted to know why the orbits of the planet were spaced as they are, and to find a mathematical pattern in their movements, a harmony of the speed, as he called it. For many years, he worked to discover mathematical relationships between planetary spacing and the time each planet took to go around the sun. In 619, Kepler discovered a basic relationship between the planet's orbit and their relative distance from the sun. We define a planet's orbit period as the time it takes a planet to travel around the sun. Also recall that a planet's semi-major axis A is equal to its average distance from the sun. The relationship, now known as Kepler's third law, says that the planet's orbital period squared is proportional to the semi-axis of its orbital cubed, or period squared is proportional to its orbit cubed. Now, what is its orbit? When P, the orbital period, is measured in years and A is expressed in a quantity known as an astronomical unit, the two sides of the formula are not only proportional but equal. 1 AU is the average distance between Earth and the sun and is equal to 1.5 times 10 to the 8th kilometers in these units. Kepler's third law applies to all objects orbiting the sun, including Earth, and provide a means for calculating their relative distances from the sun from the time they take to orbit. Let's look at each specific example to illustrate how useful Kepler's third law is. For instance, suppose you time how long Mars takes to go around the sun in Earth's years. Kepler's third law can then be used to calculate Mars' average distance from the sun. Mars orbital period 1.88 years, Earth years squared are P squared is 1.88 squared equals 3.53, and according to the equation for Kepler's third law, this equals the cube of its semi-major axis, or A cubed. So what number must be cubed to give 353? The answer is 152, since 152 times 152 times 152 equals 353. Thus, Mars' semi-major axis in astronomical units must be 1.52 AU. In other words, to go around the sun in a little less than 2 years, Mars must be around 50%, half again as far from the sun as Earth. Mars must be 50%, half again as far from the sun as Earth, I think, during its elliptical, when it's closest to the sun. Mars is closer to the Earth. Give me 1 second. Thus, Mars' semi-major axis in astronomical units, in other words, to go around the sun in a little less than 2 years, Mars must be 50%, half again, as far from the sun. Oh, as Earth is. Okay, I don't understand why they're saying that Mars must be 50% closer to the sun, unless they're talking about its eccentricity and saying at its most eccentrical point, Mars is 50% closer to Earth, is 50% closer to the sun than Earth, which could make sense with enough of an ellipsis, meaning that at its farthest, it's extremely far from the sun, further than Earth is, but when it's closest to the sun, it's closer to the sun. than Earth is. Kepler's 3 laws of planetary motion can be summarized as follows. Kepler's first law, each planet moves around the sun in an orbit that is an ellipse with the sun at one focus of the ellipse. Kepler's second law, the straight line joining a planet and sun sweep out equal areas in space in equal intervals of time. Kepler's third law, the square of the planet's orbital period is directly proportional to the cube of the semi-major axis of its orbit. Kepler's 3 laws provided a precise geometric description of planetary motion with the framework of the Copernicus system. With these tools, it was possible to calculate planetary positions with great improved precision. Still, Kepler's laws are purely descriptive. They do not help us understand what forces of nature constrain the planets to form this particular set of rules. That step was left to Isaac Newton, which we're going to get to next. So let's see where we are. Okay, so that was that. So give me a second. I wonder why. Shit. I wasn't showing. Okay, well, at least I was reading that. At least I was reading that, even though you weren't seeing it. Okay, that took a while. Oh, shit. Okay, this is a little, so what I'm going to do is I'm going to edit this and I'm going to call it part 1. And because we're not going to get all through this today. So, it seems like, so hold on. I just wanted to go back here and show this because you didn't see it all. So you didn't actually see anything. So let's just go back and review this. Okay, you didn't see this. So obviously you can see an ellipse. It's longer. It has more of a it's more oblong. And here is, we were talking about how, you know, either the Earth seems to go faster, or at least there's a degree when the other planets are closer to the sun, the planet at least seems to go faster, whereas or slower, whereas it's further away, it seems to go faster, and that can be decided with that. The point is that geometry can be used to predict exactly the speed of the planets, the location of the planets, and things like that. So, yeah, it can be used to do things like that. Anyway, I'm going to do these one section at a time. And because it is a little bit tiring, and I have been on here for an hour, or a little bit less than an hour, but I will do them a little bit at a time. So actually, yeah, that'll be it. So that actually, let's just reconvene on that. This was the laws of planetary motion. The laws of planetary motion. So we're going to keep coming back to that theme about prediction. If we predict it on the plane that we can see, we say that the science is real. But the flat earthers say that when we predict using astronomy, where we can't get out there and actually measure it, that for some reason that's not enough. Why isn't it enough? What alternative do you have? Why does it all make sense? Why does it all make sense? Why does it all make sense? Okay, I might come back today and do more, but anyway, this is the end of this one. Bye.